In this video, we are going to talk about non-deterministic finite automata. Now we look at the definition of deterministic finite automaton again, which is defined by a 5-tuple Q, sigma, delta, Q0, and F, where Q is a finite set of internal states. Sigma is a finite set of symbols. This is the alphabet. Delta is a total function from Q times sigma to Q. It is also called the transition function. Q0 is the initial state, and F is a set of final states. Now again, the delta here is a total function from Q times sigma to Q. Now for non-deterministic finite automata, delta is now from Q times sigma union with lambda to 2 to the power Q. So now delta is not a total function anymore. Now there are three differences between deterministic finite automata and non-deterministic finite automata. The first one is edges with same label can go to different states. Now this is not allowed in deterministic finite automata, but it is okay in non-deterministic finite automata. So here, for example, we have two edges with the same label A going out from state P, one going to the state Q and the other going to the state R. The second difference is the lambda transition. Now lambda is the empty word. So with lambda transition, you can go from one state to another state with nothing. So here you can, for example, now lambda transition is not allowed in deterministic finite automata, but it is okay in non-deterministic finite automata. Now this is an important thing to know, that now all deterministic finite automata are also non-deterministic finite automata. But not all non-deterministic finite automata are deterministic finite automata. Now take a look at this example. This automaton is not a DFA, but it is an NFA. Why? Because there are two edges from Q0, both with label zeros, but they are going to different states. One goes to Q3 and the other goes to Q2. So it is not a DFA, but it is an NFA. Now next example, this automaton is also not a DFA because it has lambda transition, but it is an NFA. Now in the next example, suppose that the alphabet is the set of 0 and 1, then this automaton is not a deterministic finite automaton. Why? Because from Q0, there is no edge going out with label 0. So here we have an edge with label 1, but there is no edge with label 0. So in other words, delta with Q0 and 0 is the empty set. Now the language Lm of a finite automaton M is the set of W, element of sigma star, where delta star of Q0 and W is an element of F, the final states. Two automata, M1 and M2, are said to be equivalent if they accept the same language. That is, LM1 equal to LM2. Now take a look at this example from the previous video. This automaton accepts the language of all words on 0 and 1 that start and end with 1. So that is LM equal to the set of 1W1, where W is a element of sigma star. So here, every word starts with 1. So the edge with label 0 that goes out from Q0 has nothing to do with the language. And because the only edge that goes from outside to Q3 is only the one from Q0, so this Q3 is also nothing to do with the language. And therefore, deleting this state Q3 will not affect the language. Now this time of state is called a trash state because we only need it to make the automaton determinant. So we are going to delete the state Q3 to obtain the non-deterministic automaton like this. So both the original and the new automata, they both accept the same language, and so they are equivalent. But the original one is deterministic and the new one is non-deterministic. Next example, design an automaton accepting the language in the bracket 0, 1 to the power n, where n is a natural number. So we can write this language as in the bracket 0, 1, and then star. This is the DFA from the previous video that accept the language. Now lambda belong to the language, and all other words start with 0. So the edge with label 1 from Q0 has nothing to do with the language. And also from the language, we see that each word, every 0 should follow by 1. So the edge with label 0 from Q1 is also irrelevant for the language. Now the state Q2 is also a trash and trap state. So it has nothing to do with the language, and therefore we can delete it. So we are going to delete Q2 and obtain this non-deterministic automaton. So Q0 is also a final state. Now here, that is the only one. That is because lambda, the empty word, belong to the language. So these two automata, they accept the same language, and therefore they are equivalent. The left one is DFA and the right one is NFA. Next, design a non-deterministic finite automaton on 0 and 1, accepting words which start with 0. So here are some accepted words. Now lambda doesn't belong to the language because all words should start with 0. And of course, 0 belongs to the language. 0, 0, 0, 1, they are the words of length 2. And these are the words of length 3. And this is the language. Now we start with the initial state, Q0. And we're going to accommodate the requirement that all words should start with 0. So we're going to create an edge from Q0 with 0 to another state. So this is Q1. And after that, any sequence can follow by the 0. So we're going to accommodate that with a loop label 0 and 1. And of course, Q1 is the final state. Last example. Design an NFA on 0 and 1, accepting words which contain exactly 3 ones. So here are some examples of accepted words. 111, of course. 011, 001, so there are 3 ones in there. 1, 0, 1, 0, 1, 0, 0. So again, there are 3 ones in there. And 0, 0, 1, 0, 1, 0, 1, 0, 0. Again, there are 3 ones in there. So the language is the set of 0 to the power A, 1, 0 to the power B, 1, 0 to the power C, 1, 0 to the power D, where A, B, C, D are elements of natural numbers. So we start with Q0, that is the initial state. Then we're going to accommodate the condition about 3 ones, like this. And at the beginning of the words, and at the end of the words, and in between of ones, we can put 0 or more zeros. And of course, Q3 is the final state. So we obtain this NFA.